Now I'm going to illustrate what happens to R squared as the number of parameters in your model increases. So I have some data here, okay, and I can tell you that I created this such that y does not depend on x. So it's just a bunch of random x values and random y values, and here they are, okay? And I have this graphic, and what I'm going to do is try a bunch of models, starting from the simplest model, going to a more complex model, and we're going to watch what happens to the model and to R squared. So P is often defined as the number of predictors. You have to be a little bit careful because this model doesn't have 0 parameters, just has 0 predictors. This model does have an intercept. So the model I ran here would be the mean of y is equal to beta 0, right? So there is one parameter, but I'm introducing this notation P, which is often equal to number of parameters minus 1. In other words, number of predictors not including the intercept. So here, R squared is equal to 0. It rounds down to 0 when you do this, right? Like if I don't include, well, it doesn't just round down to 0, it literally is 0. If you look at this model, the total variability in y is equal to the sum of squared residuals because x plays no role. Okay, I didn't even include x in the model. So now let's try a model where we do regress y on x. Now we know that x is not a useful predictor for y, but it would be shocking if the actual correlation between these random y values and random x values was exactly equal to 0, right? It's going to be just randomly something a little bit different than that. And because it's randomly something a little bit different than that, R squared becomes 0.01. Okay, so you can look at this red line. It does have a slope that's not exactly equal to 0. Again, it would be really surprising if you fit a line and got a slope that was identical to 0. So you get a slope that's really close to 0, and therefore a correlation that is really close to 0, but not exactly 0, and therefore an R squared that's a little bigger than 0. I'm also showing you a residual versus fitted value plot here. But the main thing I want you to focus on as we go through this set of graphics is the R squared at the top. Okay, so I can look at this and say, all right, well, x doesn't seem to be that great of a predictor for y. But suppose I continued anyway. Suppose I now chose to use the model that said the mean of y is equal to intercept plus beta 1 times x plus beta 2 times x squared. Suppose I put in that quadratic term. So what does a quadratic look like? Well, it looks like a parabola. Well, if you try to fit a parabola to the data, it's going to have a little curve to it. It would be really surprising if you had a data set where the curve of that parabola is exactly 0. So it'll be something a little different than 0. And because that curve will be something a little bit different than 0, the residuals will be a little smaller from that parabola than they were from the line, right? And because the residuals are a little smaller, R squared gets a little bigger. What if I include another term? What if I take this model and also add beta 3 times x cubed? And this is getting silly, right? We know that y is not related to x at all, let alone related with a cubic term. But if I do that, well, remember that when you draw a polynomial with an x cube in it, you start to get this kind of n shape. And of course, there is no real n shape to the relationship between y and x, but it would be shocking if the coefficients of this model were estimated to be exactly 0. They'll just be numbers very close to 0. And so you do get this little curvy n shape, which makes the residuals a little bit smaller and R squared a little bit bigger. So you can see what's happening. We're illustrating more than one of the facts that we talked about earlier. Every time we add a parameter to estimate in our model, the R squared gets a little bit bigger, right? Why is that happening? Because of overfitting. We are definitely overfitting this model. There are only 10 data points here. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 data points here. I'm already up to 3 predictors plus an intercept, or a total of 4 parameters. And R squared is only a 0.05, right? That can be a sign of overfitting when you have already up to 4 predictors, and R squared is really small. And it's just increasing a little bit each time. But clearly, you don't need a cubic term to describe this data, right? A straight line would be more than sufficient. Let's keep going. Suppose you added the x to the 4th term. There we go. You get that W shape. It's not going to be exactly a straight line. Just by chance, that would be really surprising. So it'll be a curve. It'll be an M shape or W shape, and the residuals get a little smaller. R squared's already up to 0.13, which if you were doing a social science study, an R squared of 0.13 is actually worth reporting on. People find that interesting. If you work in the hard sciences, like if you're doing physics experiments, then an impressive R squared is something really high. Right, like if you roll a ball down a ramp, you have mathematical equations to describe what should happen. And so you'd expect there to be very little noise relative to, you know, the angle of the ramp or something like that being a good predictor. But if you are in the social sciences, it's much, much harder to make predictions in the social sciences. And so in R-squared, getting up toward 13%, you know, it might be worth discussing. But here I've created that just by adding a bunch of useless terms to my model. Let's keep going. Let me add x to the 5th in my model. Watch the R-squared, x to the 6th, x to the 7th. So I now have 8 things that I'm estimating my model. My model is beta 0 plus beta 1 times x plus beta 2 times x squared plus beta 3 times x cubed, all the way up to this term x to the 7th here, right? And I'm getting this crazy curve, and you can see that the curve is getting very, very close to the data points, because the curve is not going to just be a flat line by chance. What it's doing is it's trying to minimize the sum of the squared residuals, right? What it's saying is, okay, if I have this curve with a certain amount of bumps in it, how close can I get to the data points? And the answer is really close. Look what I've done here. I have 10 data points. When I include 10 parameters in my model, an intercept plus 9 polynomial terms, now I've drawn a polynomial that goes through every single data point. Literally through every single data point. If you look at the residual versus fitted value plot on the right, you can see that the residuals are now identical to 0. So I've made all the residuals 0. When the residuals are all 0, R-squared is equal to 1, right? When the number of data points is equal to the number of parameters you're estimating, the residuals are all 0 because of overfitting, and therefore R-squared is 1. More generally, when the number of parameters you're estimating is too big relative to the sample size, right, and that's what's kind of going on here, you're overfitting. The curve is too complicated relative to the data, and I don't actually think that if someone new came in with an x value over here, that I should predict this high value over here for y. That's high only because we have this data point, this one data point here. But I don't want to be making my predictions based on just one person. I want to be generalizing. Right? The best model we saw to fit this data was this one, or maybe this one. Right? Those are the ones that generalize. But as I add these terms and make the model more complex, it looks like it fits great, but it's actually overfitting.